Hi, let's make some waves. So today we're going to introduce waves. I'm going to show you the two major types of waves that we talk about or that we're going to deal with in the class and kind of introduce the idea of how waves work, right? So let's go take a look over here at the simulation before we go any further. So here we've got a string of beads, right? And on one end is a wrench, which doesn't matter. We're just holding the bead there, and that's what we're going to use to send our first wave. And you'll see over here that our wave is going out the window. What that means is there's no end to the direction where I'm sending the waves. So I could have put them on a fixed end like this or on a loose end like this, but I'm not going to do that. Instead, I'm going to put them on no end. That way, we don't have waves bouncing back because we're not ready to talk about that yet. Okay, so let's just keep an eye on one of the green beads is fine. Okay, so I'm going to move this one green bead. I'm going to move it up and I'm going to move it down, up, down, and back to the center. Now you'll see that something happens, right? The string moves, right? Or something moves through the string, rather. The individual actual beads of the string end up right back where they started from, right? I go up, I come back down. My green bead is in the same place it was when I started, and you'll see that I sent a pulse or a disturbance through the string. See that? And there's one up and down, right? So if I start at the beginning, at the middle, and I go up, and then I come down, and then I come back to the center, this is a wave, right? You guys are familiar with the wave, right? You can make them fast, you can make them slow, you can make them big, you can make them small. You can even make mini waves. So here I am now creating a system of mini waves, and I'm trying to keep them the same size, but you can see that I'm not very good at that. So we're doing our best. Okay, now all of those waves go down the string, but then what happens? All of the particles of the string end up in the same place that they were. And the reason I'm showing you this is because it's important to understand that waves are not actually moving the thing they're traveling through, they're moving through that thing, right? So in this case, the thing or the medium that we're traveling through is this string of beads, right? But if we send a wave pulse through, all of the beads get displaced a bit, but they end up back at zero. They end up back where they started from, right? So the net displacement of each individual bead on the string is zero, right? So let's just do one more wave so you can see it. There we go. I sent one wave pulse through there. Okay. So that is essentially an introduction to the idea of waves. Okay, so we're over here now looking at the definition of what a wave is. So a wave is what we're going to call a disturbance, right? That propagates through space. I'm going to help you understand kind of what this is. So let's go back and look at our example here. We create a disturbance. Womp womp. It's going to move through this medium, this space, right? It's going to move down the string. The wave itself is the thing in motion. The particles, sure, they vibrate up and then down again, right? But the wave itself is the only thing that's really moving. And there it goes. Now, I put energy into this, right? Because it requires energy for me to move the wrench up and down. So I'm providing the wave with energy. And that wave is then carrying that energy to wherever it's going to go. So let's say that it did end up hitting something, right? It can transfer that energy to that thing, or maybe you're sitting in here because it's a water wave or something in the water park. Which remember water parks? Remember we used to be able to go outside and go to water parks. If you're in the wave pool at the water park, right? Have you ever been moved up and down by a wave? You're like one of these beads, right? But the wave also does something else. It also pushes you, doesn't it? The water particles themselves aren't moving very much. They're just vibrating up and down, right? But you, as a person sitting on the wave, are getting energy put into you by the wave, and that energy is causing you to move in a direction, right? Okay. So if you've ever been to the beach or you've ever been to the water park, you might know those things, right? You might also have heard sound waves, or there are many examples of waves. I'm sure you're familiar with them to some respect. Okay. So if we move up and down, we're creating a disturbance, and that disturbance is the thing that moves down the wave. Okay. Or moves down the medium in this case, or through space. Now you'll see that I wrote the word propagate and I wrote the word space. Propagate is a fancy word for moving. Okay. Oh, Happy New Year. Bit paper. There we go. It's a fancy word for moving. Okay. And what this really means is that the particles themselves aren't moving, but the wave itself is moving, right? That's what the propagation is. And space, you may have seen me or heard me talking about, or seen or heard other people using the word medium. A medium implies that there has to be something for the wave to move through, right? So water waves, sound waves, seismic waves, radio waves, actually not radio waves, bad example. Water waves, seismic waves, sound waves. These things have to have a medium to move through, right? Sound waves are moving through air. They can move through solids, right? Your water waves are moving through a liquid, right? Um, Seismic waves can move through solids and liquids and possibly gases. We'll talk about that later, right? So these waves can move through a medium as long as there's matter, basically. So medium means there has to be matter for these things to move through. That matter, those particles are what's going to be moving or what vibrating to cause the wave to be able to propagate, to move, right? Now, there are some types of waves, electromagnetic waves, that don't need a medium. They can travel through empty space. So we'll worry about that later, but I just wanted to tell you why I'm using this terminology. So that's why. All right, so you saw me create a wave in the string that went up and down, kind of like this picture here, right? And I dropped these green dots on here so that you kind of see where the particles are individually. And I just kind of randomly put green particles around, right? So if you were to look at one of these green particles, their motion relative to this dotted line, which we're going to call the resting position, and we're going to call that 0. Let's label it 0. There we go. That 0, that resting position, would be where those beads or those dots would be if there was no wave moving through the medium, the string that they're a part of, or the water that they're a part of, or whatever, right? So normally that would be like this. So if we're in the ocean, these are water waves, and if there was no wave moving through the water, it would just be flat on this dotted line. Okay, makes sense. So this is a specific type of wave, and in this case, you can see that the particle, that is the ugliest color. Let's change it to something prettier. There we go. Particle motion is up and down. Whereas the wave itself, the wave starts here, right? So we're moving the wrench up and down. Let's go back to our wrench example, actually, and just look at it, right? So if we move the wrench up and down, we're moving our particles up and down, and the wave is moving which way? Hopefully you said right, right? So the wave itself is actually going to be moving left to right. So what's interesting here is that the particles are moving perpendicular, okay, to the direction of the wave. They're moving in, the particles themselves are vibrating, and let's change this. Instead of saying motion, let's say vibration. Particle vibration, because they're technically not moving, right? They're getting displaced up, but then back down, and they're ending up having a 0 total displacement. So particle vibration is up and down, and the motion of the wave itself is actually to the left or the right, or both. Okay, this is a specific type of wave, and this type of wave is called a transverse wave. This is a transverse wave. All right, excellent. So that one's transverse. Now there's another type of wave that you guys know a lot about that we're going to talk about next. Okay, so before we can start talking about our next type of wave, let's draw in a side view of a speaker. Okay, so this area here, let's erase a little bit. We'll make little dips. This, make another little dip like this. Actually, let's just make it one big speaker, huh? So it's gonna be a big speaky boy. Okay, so how a speaker will work, right, is usually there's a little bit of a diaphragm over top of whatever is back here that's causing the pulse, right? And this thing is actually going to be pulsing back and forth. Going to be pulsing back and forth. So it might actually vibrate. And if you have speakers or you've ever put your fingers on your earbuds, you might know that, right? So there's a pulse that goes back and forth. And what happens is it's gonna vibrate the particles in the air. Okay. So when it pulses forward, it's going to take the air particles that were in that space and it's going to push them together, right? Kind of making them packed really tightly. There's your air particles packed really tightly, right? Now, what happens next is it's going to draw back. And when it pulls back, then the air is going to be nice and loose, right? So this section of particles is going to be pushed away, and then we'll have a loose section where there's not as much density. And then there will be another wave pulse where you have densely packed particles, right? And the densely packed particles that's what's basically forming your sound wave, right? So let's just flesh this out a little bit. This is a loose area, this is a dense area, this is a loose area, this is a dense area. Okay. So this is basically how a sound wave works. Now, this is a bad drawing, is not to scale, etc. The sound is actually going to expand as it moves outward. We'll worry about that later when we start talking about diffraction. Okay, but let's just talk about this for now. Okay. So what we've created here, the same thing can be seen in a slinky. Let me just show you it on a slinky. Let me use my gray because slinkies tend to be gray. All right. So this is one way to show it. This is exactly the same way to show it. So slinkies are normally tightly packed like this, right? And if you pull back on one side of the slinky and you stretch it out, and then you have a couple coils, and then you let go and it springs back in, right? What's going to happen? This whole section is going to then move forward, right? Passing energy through the rest of the slinky. And what you're going to see, is a tightly packed section and then a looser section. And then if you keep making those little wave pulses, you'll then see another tightly packed section and then a looser section and then a tightly packed section and then a looser section in your slinky, right? Now, this is, of course, the world's most beautiful drawing of a slinky, but here you can see one wave pulse. Here's another wave pulse. Here's another wave pulse, right? And then here in this middle section are things that are where the wave is essentially not at right now, right? So these waves are going to travel down your slinky and they might bounce off of something, come back, right? So this is a different type of wave. This is caused by compression, okay? So compression is actually sometimes in the name of it, right? So this is called a longitudinal wave, also sometimes called compressional. Now, what's interesting about this is, and this is the best place for this, right? The particles themselves are moving left and right, right? The wave is also moving left and right. So the wave could be moving up and down as long as the particles are moving up and down. It's still longitudinal. Longitudinal waves, the particles will vibrate in the same direction as the wave travels, or that the wave travels. As the wave travels. Don't tell your language arts teachers, guys. That the wave travels. All right. That's a wrap.